Hello guys and welcome back to my video. So in the last video we talked about convolutions. In this video we are going to talk about padding, pooling, and then the fully connected layer. So we can see I have this formula. This formula determines our output after a convolution. So it says that number of the output matrix is equals to the input plus 2 multiplied by the padding minus the kernel size, which is our convolving filter or filter size divided by the stride. Remember, I said that the stride is the amount of pixels by which our filter moves, right? And then we add by 1, right? So going further, right? So padding, as you know, as we applied convolution to deep images in deep neural networks, is that we tend to lose pixels on the parameter of our image. Since we will be using these small kernels or these small features for any given convolution, we lose few pixels but it might add up as we apply many successive convolution layers, right? As you know that since we are doing deep learning, we have successive layers, right? So let's say if you convolve an image, right? If you convolve an image, it becomes, let's say, if you convolve a 6 by 6 matrix image by a 3 by 3 filter, it becomes a 4 by 4, right? As you can see, as we'll be convolving these images in the neural networks, they become smaller and smaller, so we'll be losing pixels. So to solve this problem, we use what we call padding. So what is padding? So padding is simply applying zeros to the edge of an image, right? So in this case, we have a 1 by 1 padding. So that means that we have added one layer of zeros at the top of the image, right? If it's a 2 by 2, that simply means that we have another layer at the top of these zeros. We have two layers of zeros, right? So let's take a look at this, right? Let's say we have a 6 by 6 filter, right? We have an input image, which is a 6 by 6, right? We want to determine the output. We know that it's 6 minus 2. In this case, we have a padding of 0 plus 3. We divide by 1, so it doesn't make any difference, plus 1 according to our formula. You can try it out. We'll get a 4 by 4 matrix, right? So you see that when you convolve a 6 by 6 matrix by a 3 by 3 matrix, we get a 4 by 4 matrix, right? That simply means that we have lost some pixels. So if we go and convolve again, you'll see that our image is becoming smaller and smaller and smaller and smaller, right? So now we go back to our issue, right? There are two types of padding. We have valid padding and we have SEM. Valid padding simply means that there is no padding. Whatever deep learning library that you are using, when you see it written valid padding, just know that there is no padding, right? But SEM means that we want the output of our convolved image to be the same as the input, right? I hope you got that. We want the output of our convolved image to be the same as the input. Let's take a look at this. If we want the output of our convolved 6 by 6 matrix to be the same as the input, what padding do we need to use? Since we know that we say that n out, n now, since the output is now equal to the input, right? The output is now equal to the input minus 2p, right? Plus 3 plus 1. Right. If we do that, you get that we'll get 0 here, and then these n they cancel out, and then we get negative 4 is equals to negative 2p. So now it's telling us that we need a padding of 2 so that we need a padding of 2, right? So that we can get an output that is the same as the input. So you just play around with the formula. So that's what same padding means, right? You want the output of the convolved image to be the same as the input, right? So moving on, we are going to take a look at what we call the max pooling, right? Guys, remember that when you are dealing with images, right, images are highly dimensional. That means that we want to reduce the weights of our neural network. Otherwise, our neural network will get very, very big, right? So the pooling step downsamples the convolved images. This reduces processing time and image size. This reduces overfitting if our network is given too much information that is not relevant to classifying the image. In max pooling, a window passes over an image according to a set stride value, and the maximum value within the window is pulled into an output. So let's take a look at this, guys. So here we have our input, and then we have our pooling matrix, right? So it moves with a given stride. Let's say the stride is 1. So if it starts here, what is the maximum value? It's 8. We then print out 8. It goes on to the next. What's the maximum value? It's 6. Here, what's the maximum value? It's 9. Here, what's the maximum value? It's 9. That's what max pooling does, right? It pulls out the maximum value, right, into each of the matrices, pulls out the maximum value, and then we print out those maximum value. As you can see here, we have a filter of a 2 by 2, and then we have a stride of 2 by 2. So if we start here, if our filter starts here, right, what's the maximum value? It's 9. It prints out 9. It then moves here. What's the maximum value? 7. We move downwards. What's the maximum value? It's 8. And then we move to the right. What's the maximum value? It's 6. Then we have what we call average pooling. Now, average pooling differs from max pooling in that we have a filter here. It then calculates the average of these numbers in each of our in each of our metrics, right? 9 plus 4, 9 plus 4, that's 13, plus 2, that's 15, plus 2, that's 17. You divide that by 4, you get 4.25. We do the same, we move to the right, we do the same, calculate the average. We move downwards, we calculate the average. We move to the right, we calculate the average. So that's what pooling does. We have max pooling, and then we have average pooling. So when we'll be using these deep learning frameworks, when you see max pooling, just remember this video. When you see average pooling, just remember this video, right? So now after this, we now have what you call the flattening, right? So after multiple convolutional layers downsampling operation, the 3D representation of the image is processed and is passed into a multiple layer perceptron to output probabilities. So we have this pooled feature, right? We then flatten this into a one-dimensional array. As you can see, this is a 3 by 3 array, but this is a 1, right? This is a 1 by, we have this is a 1 by 6, right? This one, we have flattened our neural network. That's what the flattening layer, right? We have flattened it out, right? And then as a whole, this is the fully connected layer. We have what we call the fully connected layer. This is the fully connected layer. So if you've not watched my video on how to create a simple neural network when you use dense layers using keras, this will be the fully connected layer will be dense neural network, right? If you have not watched that video, please revisit that video and watch that video again. Now we have a full convolutional neural network, right? We have an image, we have convolution here. Convolution determines our feature maps. We then pass it through an activation function, which is ReLU. We then perform max pooling, right? We flatten the data, we pass it into our fully connected image. Right, so guys, this is how a convolutional neural network works. I hope this video helped you to grasp the concept of how convolutional neural networks work. So please, guys, if you find this video useful, please click on the thumbs button up to help the algorithm to suggest the video to more people. Share this video, guys. Share this knowledge, right? And also watch my previous video on convolutions if you have not watched it, guys. We meet here next time, guys, when we'll be implementing convolutional neural networks using keras. Thanks for watching. Cheers.